In this lecture we talk about Huber rings or f-adic rings. So to understand Huber rings or f-adic rings, one first needs to understand the topology of a ring and completion of a ring. So the easiest source to learn this is A.T.N. McDonald's chapter 10 and page number 100. So easy to remember, chapter 10 and 10 square 100. So you can open that, and first two pages will give you all the information you need to properly appreciate the depth we are going into. So we say A is a topological ring if A is endowed with a topology such that both addition and multiplication are continuous maps. So that is, you're going from A times A, take a factor here, take a factor here, add them, multiply them. That is just a continuous map. And this A times A, you just give it a product topology. So that is the standard definition of a topological ring. So we will go through a large number of terminology which is used in Huber rings. So first is adic. So ring A is called adic if there exists an ideal I of A such that this I to the power of n lies in natural numbers. So you keep multiplying this ideal by itself, and this will form a basis of neighborhood of 0. So this is a linear topology. You just need the basis of neighborhoods of 0, and for any other element you just add that constant to it and you come to that element, and this neighborhood will shift to the neighborhood of that element. So this is just a linear topology. So again, you just need the basis of 0, and then you can transfer it by adding a constant to any other point in the ring. So this neighborhood. So such an ideal I which forms the basis of neighborhood of 0, and by linear topology, just by linear translation, therefore neighborhood of every point, this is called the ideal of definition. So standard example, you have p-adic integers and the prime p forms the neighborhood. Now we come to the Huber ring. So ring A is called f-adic or Huber. So this F stands for finite. So this will be clear in a minute. So if there exists some A0 which lies within ring A, this is an open adic subring. So basically all the elements contain all the elements have their neighborhood contained in this ring. So all the neighborhoods are inside this ring. So this is called the ring of definition of A, and if it has a finitely generated ideal of definition. So this I is the ideal of definition, but it is finitely generated. So this finitely generated is what carries to this F here, finite. So finite adic. So your ideal of a definition is finitely generated, and there is a ring A0 sitting inside. So for example, so you have three things, A, A0 and I. So you have this QP, ZP, P. So p-adic rationals, your ring of definition is this, and then you have P as the ideal of definition. So again, you could have just taken ZP, and then this A0 would have been equal to A. So again, this triplet here is this triplet here. So two examples. Now we talk about a bounded set. A subset S of ring A is bounded if essentially you can fit this subset into the neighborhood of 0. So a set S of some ring A is bounded if you can force it into a neighborhood of 0. So that means that for every neighborhood U of 0, there exists a neighborhood V of 0 which when multiplied with S will force it into U. So V times S, V is in this neighborhood V, S is in set S, and you multiply them, you are forced into set U. So now we talk about power bounded element. So an element A in the ring is power bounded if you can write it as A to the n is greater or equal to 1, this set is bounded. So that means the powers are bounded, that is, you can fit it in the neighborhood of 0. And then you define A, this circ. This is all the elements of the ring such that this element A is power bounded. So this is all the power bounded elements. You call a ring uniform if this thing which we have just defined, ring of power bounded element, this is bounded. Now we talk about topologically nilpotent. So an element A in the ring A is topologically nilpotent if you take the limit of this element A n, it goes to 0 as you raise the power to infinity. So this A circ is that all the elements of the ring A which are topologically nilpotent. Now we talk about analytic. So if topologically nilpotent elements generate the trivial ideal of A, we call the ring analytic. So that is again topologically nilpotent elements. They can generate either the zero ideal or the entire ring A. So because the ring A has only two trivial ideals, 0 and the entire ring A. So now we come to important remark. This remark will give us a proper characterization of this A0 and this. So first you have put a multiplicative seminorm on the ring A. So if this is a multiplicative seminorm on the ring, then A circ is just this. All the elements of the ring whose seminorm is less than equal to 1, and this double circ is all the elements of the ring whose this seminorm is less than 1. So you have less than equal to 1, you have less than 1. So you can think of this as the maximal ideal of this ring. So Tate ring. So this ring A is called a Tate ring if it is Huber, so that is it satisfies your finitely generated ideal and has a topologically nilpotent unit. So you have this and you have this. So you combine this thing with this thing, you get a Tate ring. So example, this QP and this unit P, which is topologically nilpotent. So not only P is topologically nilpotent, it is also a unit. So it is Huber and it has topologically nilpotent unit. So notice that we have added this word unit here. Now we talk about pseudo uniformizer. So let K be a topological field that is complete with respect to a non-trivial, non-Archimedean metric, this. So then K would have an element like this. So this is var pi. So this seminorm of this is less than 1. This var pi is lies in the units of K. This is called the pseudo uniformizer. So we have just told that when this pseudo uniformizer would exist. So you take a topological field and it has non-trivial, non-Archimedean metric, then you will have a pseudo uniformizer. So now let us come to some examples of these Huber rings. So these three I have copied here. So we have already given two examples. Furthermore, you take this K as a topological field, then this A0 is just this K circ, that is this right here, and your ideal of definition is just the pseudo uniformizer. Now again, Tate ring. So let us first show you what Tate ring is. Let us now define Tate rings. So Tate rings are written like this, but they are just elements of power series. So this I is a multi-index. So this Ti represents this multi-index from here, and these are elements of these power series from here, such that this coefficient goes to 0. So this coefficient I, as I said, is multi-index. So this Ai would essentially mean sum of all the elements in here. So just this I1 plus I2 all the way to whatever power you have. So this is what this will go to infinity, then this Ai should go to 0. So this gives the example here. So you have this power series, and then you have, so this K is the topological field that is complete with respect to a non-trivial, non-Archimedean metric. So you have this K, and then you have this K circ, and then you have this pseudo uniformizer, the same thing which comes here, because this is the same K. Then another example could be ring A with discrete topology. So then you just have A, and 0. The 0 is the ideal of definition. Ring of definition is A. Then you can talk about power series like this, and this is the ideal of definition. And then again, for this K topological field, you can talk about this K circ power series like this. And then you have exactly the same thing here. Now instead of a ring A, you're replacing with K circ. So now you have a pseudo uniformizer right here, the same pseudo uniformizer that is here. So now let us note down two more important things before we close this lecture. So first is Huber pair. So Huber pair is generated by A plus. So this consists of a Huber ring A. So this is the Huber ring A, and this A plus lies within this A circ. So this A plus is an open subring of A that is integrally closed. So you can think of ring of integers here. So A plus, you can think of it as ring of integers. So for our examples here, so we are considering this A plus as this A circ, and for you can consider all these examples also examples of this Huber pair if you just put all three of them equal. So that is A circ is equal to ring of definition, which is also equal to this A plus, that is ring of integers. But in general the relationship is like this. So there are cases when all three of them are not equal. In fact, A plus is actually a inductive limit over all rings of definition. So this is actually an inductive limit over all such rings of definitions. So now we have talked about Huber pair, we have to talk about morphisms of such pairs. So a morphism of Huber pairs from A plus to B plus, this is nothing but a continuous ring homomorphism, as you would have expected, phi from A to B, such that this phi of A plus lies within B plus. A ring of integers of A plus gets mapped within B plus. And this morphism is called adic if we have the following conditions on the ring of definition and the ideal of definition. So the ring of definition should lie within B0, and the ideal of definition, which is sitting in A right here, this should be the ideal of definition here also. So that means this phi I B0 is the ideal of definition of B0.